For decades, scientists have had this massive goal to create a perfect digital copy of a living thing. A simulation so good, it would be indistinguishable from the real deal. And for their first target, they picked a creature that honestly seemed almost ridiculously simple.
So you see this headline from Wired magazine about the Open Worm project? Utterly failed? Wow, that sounds pretty final, doesn't it? But is that really the whole story? Or did this so-called failure actually uncover something incredibly profound about life itself?
Okay, so this is our subject, the tiny roundworm, C. elegans. It's just 1 millimeter long. But here's the crazy part. We know pretty much everything about it. We have its entire genome mapped, we know the exact number of its cells, 959 to be precise, and we have the complete wiring diagram of its 302 neurons. I mean, it is the most well-documented organism in history. Simulating it should have been a slam dunk.
And that is the central mystery we're digging into. If you have the complete blueprint, right, and the full wiring diagram, why can't you build a working model? What piece of the puzzle are we missing? Well, it turns out we were looking at the entire problem in completely the wrong way.
The first big breakthrough came from a realization that seems obvious in hindsight. Life isn't just a string of information. It's a physical, mechanical system, and is governed by a set of rules that, for a long time, scientists had almost totally ignored.
Yeah, the initial approach was pure computer science, really. The idea was, let's map every single neural connection, every synapse, and treat this worm like a biological computer program that we just need to reverse engineer. The assumption was, if we get the code and the wiring right, we can just hit run and a little virtual worm would spring to life. But it didn't. Not even close.
And this leads us to this incredibly important concept, mechanobiology. It's the science of how physical forces, pushing, pulling, squishing, actually shape living things. This field tells us that the body isn't just some passive machine run by genes. It's an active participant in its own construction.
And it's wild when you think about it. Cells are constantly sensing and reacting to their physical world. They don't just follow chemical signals. They can feel how stiff or soft a surface is. They react to tiny little bumps and grooves. They stick to each other. They get pushed around and crowded by their neighbors. The physical world isn't just a stage for life. It's a dynamic scaffold that's actively shaping how it gets built.
So the bottom line is this. The software, the genetic code, is completely inseparable from its physical hardware. You can't just simulate the brain's wiring in a digital void, because the way those neurons connect and fire is directly influenced by the physical tension and the squishy reality of the tissue they live in. The hardware is constantly shaping the software, in real time.
This realization forced a complete U-turn. Instead of trying to take a finished product apart, scientists started asking a totally different question. How does life build itself from the ground up, often without any central plan or blueprint at all?
And the answer lies in this absolutely beautiful and powerful concept called emergence. This is the idea that you can get mind-boggling complexity, not from some master architect, but from tons of simple things, like cells or ants or termites, each just following a few simple rules and interacting with its neighbors.
Termites are the perfect example of this. No single termite has a blueprint for one of those incredible cathedral-like mounds in its head. Not a chance. All they do is follow a couple of super basic rules. Wander around, drop a little pellet laced with a chemical trail, and, oh yeah, be attracted to the trails left by others. That simple feedback loop is all it takes for these magnificent, complex structures to emerge. It's all bottom-up, with no boss inside. And this same idea applies to how an embryo develops. For years, biologists were stumped by something called the French flag problem. Basically, how do cells know to form patterns like blue, white, and red stripes? The old school view was that it was top-down, that cells read some kind of chemical map to figure out their pre-assigned spot. But the emergent view says no, there is no map. Instead, the pattern arises out of a constant, dynamic conversation between the cells and their environment. It's adaptive, not pre-programmed.
So if life is just too complex to reverse engineer, what's plan B? Well, some researchers came up with a pretty radical new approach. If you can't deconstruct it, maybe you can just build it yourself, from scratch.
And this slide just lays out the two fascinating ways people are doing this. On one side, you've got brain organoids. This is where you basically coax stem cells to self-organize using those same emergent properties we just talked about. It's like planting a seed. You get something incredibly complex and lifelike, but you don't have a ton of control. On the other side, you have these engineered neurosheets, which is basically like building with biological Legos. You literally bioprint the exact circuits you want onto a sheet.
So what does this Lego approach get you? Well, it gets you control. A ton of control. You can design, print, and then literally cut and fold these sheets into whatever 3D shape you want. This lets scientists build the precise neural circuits they want to study, completely bypassing the messy, often unpredictable process of natural development.
All right, so let's circle back. Where does all this leave us on our quest to understand that tiny 1-millimeter worm? It leaves us, I think, at the dawn of a new and, frankly, much more exciting science of life.
You know, that headline about the utter failure, it got it completely backward. The inability to simulate the worm just by mapping its parts wasn't a failure of the project. It was a failure of an entire way of thinking. It forced science to finally admit that a living thing is so much more than just the sum of its parts.
And this is the fundamental shift we're talking about. We're moving away from reductionism, this idea of breaking things down and searching for the one gene for this or the molecule for that. Instead, we're moving toward a complex systems approach, where we study the dynamic dance between genes, physics, and the environment, all at the same time, across every scale.
So the ultimate takeaway here is that the goal isn't to find a simple model for life anymore. The real goal is to build brand new tools in math, in computing, in engineering that are actually powerful enough to grapple with the true, messy, irreducible complexity of living systems. We have to learn to meet life on its own terms.
And that leaves us with this one kind of huge final question. As we learn these fundamental rules of biological construction, are we just getting better at engineering life? Or are we finally learning how to truly collaborate with it?